a binomial coefficient perspective is 1C1. This entry here is on row 2, so it's 2, and it's the first entry at position 0. This entry is on row 2, but now it's at index 1, and this entry here is on row 2, but it's index 2. Index 0, index 1, index 2. We always start counting at 0. Right? The next one is, well, maybe I should have really, let's ignore that here. Maybe I should have really done this over here to make it a little bit bigger. This is on row 0, and there's only one entry, so it's at index 0. Okay? The next one is on row 1, okay? And this is index 0. This is still on row 1, okay? And this is index 1. This here is on row 2, and this is index 0. This is on row 2, and this is index 1. This is on row 2, and this is index 2. This here is on row 3. It's the first one, so it's at index 0. This is on row 3. It's the second one, so it's at index 1. This is on row 3. It's the third one, which is index number 2. And this is on row 3, and it's at the one that's index 3. Finally, this is on row 4. This is row 4, 0. This is row 4, the first index. This is 0th index, the first. This is index 2, row 4, index 2. This is row 4, index 3, and this is row 4, index 4. Actually, my point is this, is that if you calculate every single one of these, if you calculate all of these particular values, okay, using the fact that NCR is equal to n factorial over r factorial times n minus r factorial, you'll get each one of these numbers. That's 0C0 probably looks a little bit strange. Let's have a look at it in the formula. So 0C0 is 0 factorial all over r factorial, which is 0 factorial, times 0 minus 0 factorial, which is the same as 0 factorial all over 0 factorial times 0 factorial. Now, 0 factorial by definition is 1. So this is the same as 1 over 1 times 1, which gives us 1, which is equal to 1, which is what we had here. Right? This particular term here, okay, this particular term here is associated with this. This is associated with this, and so on. And that's the relationship between Pascal's triangle and these binomial coefficients. Okay? My point is this, is that when we looked at the expansion, okay, when we looked at the expansion of x plus y squared, okay, so let's just look at the expansion of the expansion. Okay, we'll get to a nice, more complicated example now in a minute. The expansion of x plus y squared. When we expanded that out, what we got was we got x squared plus 2xy plus y squared. Now, the exponent here is 2. Let's go back to Pascal's triangle. 1, 1, 1, 1. Sum d is 2. 1, 1. Sum d is 3. Sum d is 3. 1. Okay? This is of power 2. So what we're going down to is row 2. Well, that's row 0. This is row 1. And this is row 2. And you can see that these coefficients here, the 0 is the one that's here. The 2 is the 2 that's here. And the 1 is, there's a 1 here. So if I want to calculate x plus y cubed, I need to look at the third row. Okay? And the third row's coefficients would be 1, 3, 3, 1. And don't forget the fact, yeah, okay, that all the terms, okay, all the terms, the first term is going to start off with the power, okay? The last term is going to have the power, okay? And then each term in between is going to be, we're going to reduce this, okay? So this is going to be an x squared, but because I've reduced it by 1, I have to put in a y to the 1. This is going to be an x times a y squared, okay? And this is just going to be 1y cubed. So my point is this becomes x cubed plus 3x squared y plus 3y squared plus y cubed, okay? Which is what you'd get if you expanded this out, let's say, like this. Okay? So we know that this is the same as x plus y times x squared plus 2xy plus y squared, okay, which is the same as x times that gives us x cubed, x times this gives us plus 2x squared y, x times this gives us plus xy squared, y times this gives us plus x squared y, plus y times this gives us plus 2x